Thank you, Anthony, as always, and the team here. And this is, just talking to Mohit, the most nerdy topic in the history of Westwood Lectures about non-convex optimization, something I personally feel passionate about. But we also happen to schedule this right before the holidays. So I said, Mohit, I applaud your audacity. You are a bold person, intellectually bold, to talk about an important and nerdy topic right before holidays. So this is the fourth and the last Westwood lecture for this semester. And we've had a great tradition started by Mitch Daniels to bring a small group of colleagues, talk about topics across different disciplines. And in almost all cases, I have no idea what they're talking about. Today, probably after all these years being an administrator, I have no idea what you're talking about anyway. But I used to study the easier version, the convex optimization problems. As one of my co-advisors at Stanford was Stephen Boyd, and he wrote the textbook, took his class, did research with him, and then did not end up following optimization OR path, IE path, but more of myself, engineering and communication network path. So to those who are here and those going to watch on video here, I tell you this is a fascinating topic here. Now, Mohit wears two different hats. He's also the Executive Associate Dean. Okay, did I get the title right?
Yes.
Executive Associate Dean of the Mitch Daniels School of Business, and been working very closely with Dean Jim Bullard. And he was actually the interim dean for a while in between, and has been doing an amazing job as administrator as well. So this talk is a proof, is a crisp, sharp proof that strong administrators can actually keep research alive as well. So with that, welcome Mohit, and thank you very much.
Thank you, President Chiang, for the invitation, and thank you all for being here. As Mung mentioned, the topic is going to involve quite a bit of nerdy mathematical slides. I don't intend to get into any of that unless a lot of the audience wants me to. So what am I going to talk about today? As Mung was saying, convex optimization is a field where it's like you're making a toast. You see the bread browning slowly, and you know you're getting closer to it getting done. With non-convex optimization, the feeling is a slightly different one. It's more like the experience I had yesterday. So as I was preparing my slides for this talk, the panic monster had finally set in and said, okay, you need to get ready for the talk tomorrow. So as I was preparing my talk, what happened was the internet went down. And so the internet went down. I said, okay, what should I do? I went and checked my router, checked my access point, checked all of the different things, rebooted my computer, tried to see all of different types of things, and none of those were the problem. So I ended up on a service call asking our provider if their service was down. It turns out that there's an optical network terminal right outside my house that needed to be reset. And so after a long call, I figured out that that's what is needing to be done. So none of those previous actions, lots of actions, none of those previous actions necessarily told me where the actual solution is. And that's sort of the challenge that we deal with in non-convex optimization, and how can we sort of make it more like the bread toasting type of experience. So that's the question that we are sort of dealing with. The question then is, what has got me interested in this field? It feels like you're always solving a lot of puzzles, and in each of those puzzles, the question always is, gets more and more challenging, but there are lots and lots of applications. And so I want to talk a little bit about some of the concrete applications that we've been looking at and how they have governed some of the theoretical work that we've done in the space of non-convex optimization. So my first context that I want to talk about is that of chemical separations. So what is this all about? So what we do is in order to separate chemicals that come up that are mixtures of chemicals really, so like crude, you boil them and you separate them into different components. So that's how you get gasoline, that's how you get different kerosene, diesel, and so on and so forth. The question that comes up is how important is this for our economy? 2.5% of US energy is actually used in separation processes in the chemical industry. So 2.5 quads of energy, roughly 100 quads is what US uses. So 2.5% of the energy is used in this, and 90 to 95% of the separations, liquid separations, are done by distillation. Some gas separations as well. So what happens when you actually start to do distillation is that there are various choices in how you boil these liquids. So if you take the crude and you decide to separate, and this crude consists of lots of different compounds. So as you boil them, different compounds have different boiling points. They rise up, you can separate them away. So if you start with 4 components together and you separate them in a certain sequence, you end up spending a certain amount of energy. And where does this energy come from? You're burning some fossil fuels, you're heating up these large towers of liquid, and let's say you spent 1 unit of energy doing this. If you did the same separation in a slightly different way, you'd end up sort of spending 0.64 of the energy, and so it'd be 36% less energy. So the choice of how you boil these fluids, how you make them go through different towers, makes a huge difference. Similarly, how much flow you draw on every different piece has a big difference in terms of what it ends up creating in terms of energy requirement. Now, if you can reduce the energy requirement of this process, even by 10%, this is about 200,000 barrels of oil per day that's sort of used in this kind of a process. So, and the corresponding amount of carbon dioxide that you release is also getting reduced. So this allows for more sustainable operations. At the same time, it reduces the energy needs. Now, a completely different area is that of communication networks. So in communication networks, as companies like Meta and Google, and this is an area that Mung is quite familiar with, communication networks is an area where what we are trying to do is ensure that these networks perform and can send all the traffic that we want them to send, even though they might have some failures, which are a common occurrence in these networks. So you think of networks, links fail, somebody drills a hole into some fiber optic cable, right? So there is a failure, or just one of the network equipment, like my optical network terminal, had a problem. So one of these things fail, and now you still want to be able to send the demand. So what the companies are interested in is figuring out how to design, how to route traffic over these networks that will ensure that these networks are capable of handling a bunch of failures that can occur during this process. Yes?
Is that what you're aimed at, trying to reduce the number of failures?
No, the failures are occurring, and you want to design your network in a way. So there are two different parts to this. You want to design a network in a way that can still service all the demand that you want to send, despite a certain number of failures occurring. The second is, for your given network, you want to be able to certify to your customers that you will be able to send. And so those are the two types of questions that you usually are dealing with.
I want to do this in
Yeah.
cost. Sorry. But then if that link is not necessary to essentially connect SMT, why would we even start designing a network with that link? Why bother when it's clear that it doesn't serve a useful purpose?
No, so first the network exists for servicing a certain amount of demand. So this network, for example, if you wanted to send 3 units of supply from S to T, it can service that. The question is, when some failures occur on certain parts of these networks, are they still able to send the amount of traffic that we wanted them to send? And that sort of a guarantee helps the customers who are actually sending the traffic to be more comfortable with the service that you can provide as a network provider.
Okay.
Right?
So I guess there's some service level here, right? So
Yeah, it's sort of a service level agreement. Yes, absolutely. And then there is a third sort of pricing oriented context. And so companies like to set up bundles of goods and sell them for some price schedule that they put together. Now, you can have an interesting sort of bundle where you're given some pizza, but also get some antacid and a gym membership, right? So with those kind of bundles, how should they be priced, right? Or what can you do with pricing such commodities? Now, the question that comes up here is actually a very hard one. APX hard is a terminology that computer science uses to say, we don't know how to solve this problem in any efficient way, but neither does anybody else in this world. So in some sense, the question here is how to price goods so that you can extract the most surplus from customers. In its most general form,
You're solving this from the point of view of the supplier.
this is, you're solving it from the point of view of the vendor who is selling the goods.
All right, and the vendor, let's just get this, the vendor is attempting to maximize something.
Is trying to maximize their profit.
Okay.
Yeah. And so their pricing, people are choosing based on their preferences once the prices are given. And the question is, how do you price so that they maximize the profit? So that's the question. And the problem in its most general form is hard, but there are instances where, so Spence in 1970s and in 1980 proposed a Spence mirrorless condition, which is essentially saying that customers are ordered in their preference. So there are customers who like this product that you're trying to sell a lot more than others. And what we are looking at, really the bundles that we are talking about are those which consist of, can you buy 3 units of this, or 4 units of this, or 2 units of this, and how should the pricing structure be? So that's one type of problem. How many gigabytes of data do you want with your service plan? 2 gigabytes, 10 gigabytes, 20 gigabytes. So how should those be priced? This is essentially the idea that how can the vendors extract consumer surplus and provide services that more the customers who like the product more will gravitate towards getting more of it. So if Mung was to get ice cream, and how can we get more? How can we have him buy more of ice cream? than
That's
what
not a
we
hard
might.
problem.
That's not a hard problem, right? So more of ice cream, but also pay more somehow for it. So that's the basic idea of what is done. And the products that you're dealing with, some of these products also have this no disposal type of cost. So essentially what happens is as you give them more and more, their valuation actually goes down. So even that can happen. I'm guessing if some of you have started to see how our new systems will be, elements and others, you might wonder, do I really need all that complexity in my process of doing my activity report, or could I be done with a little bit less in terms of services? So those are the questions. For some, this is good. For others, they don't really care for the extra features, and their value actually goes down. So that's another one of those problems that we've been looking at. So as I said, what is the challenge with these problems? The challenge with some of these problems is that you're trying to find the optimal solution, which is sort of minimize cost, maximize profit, but the terrain that you're looking at is highly non-convex. And so when you are at a solution, you don't really know whether this is the solution that is optimal, or there is another solution somewhere far that might be much better than what you have in your current.
What you're trying to do here is figure out whether you're at the optimum.
Yes. So the question for us is how, if we are at the optimum and if we are not, how do we get there, right? So that's basically the main thing. So now.
Could you go back to the previous class? Apologize. So you're trying to figure out which of those curves you're on, or bumps you're on, and you're trying to get to the top one. Is that
top one or the lowest one, depending on which direction you're looking at, right? And so that's what we are trying to do. And most of these problems have high amount of non-convex behavior. So that's the goal that we are trying to solve. And so so I want to sort of give a little bit of a background on this, on what has happened in optimization over the last couple of decades. So 3 decades ago, if you were to sort of talk about optimization and as we were talking earlier, the question would be often, what is it? So if you talk to people and said you work in the area of optimization, the most common question you would get is something like, what do you optimize? And at that point, a lot of us who were working in this space of optimization would think, this is like as if you are a chef and you tell somebody that you're a chef and the person asks you, what kind of sandwich? Right? So the point here is that there are some tools, just like it is for chefs, the knife skills, whatever things they are developing is really what is driving the change. Similarly, in optimization, there are some foundational techniques and methods that are being built that apply to a large class of problems. And I want to talk a little bit about why those 3 very different looking problems have some similar features that allow us to do certain things. There has been a lot of progress in optimization over the last couple of decades. What has happened is that, so just to give a context, if you think about the most commonly seen progress, that is in terms of computers. So the computers which were in 1989 to 2023, you can think of the scale up in speed due to Moore's law or whatever else is about 1,700 or 2,000 times faster. So computers have got about 2,000 times faster, let's say. And that's why the cell phones today can do a lot more than what desktops could do long time ago. On the other hand, if you look at what has happened to mixed integer programming, and this is actually the slide from this is a graph created by Gurobi, which is one of the main integer programming software, you'll see that they estimate the change in algorithmic speed independent of the change in computing speed is about 3.7 million times. So when you put those two together, because indeed your computers are faster by 2,000 factor and 3 million factor of algorithmic speed changes, what can now be done in a minute would take so much longer previously. So this is often not as well appreciated, the fact that algorithmic improvements are probably significantly larger than what the computing level improvements we see. And the end result, what we see today, is the cumulative effect of that. And the optimization is behind a lot of the AI and data science algorithms that are going on behind. A lot of these are benefiting from all the advances that have occurred in algorithmic development. Now, for the non-convex nonlinear optimization, this is relatively more recent. In fact, the solver we wrote was one of the first solvers that could solve these problems, and is widely used. So that's Baron. And recently, this was a recent study from a competing group of solver creators. And what they show is that now more and more solvers are starting to become competitive in the space of non-convex optimization. And solvers such as Gurobi, which were previously in the mixed integer programming, have started to adopt now the nonlinear programming space as well. So I want to talk about a quick idea on what makes these algorithms work. And so at the heart of these non-convex optimization algorithms is the process of what we call relaxations. And the way to sort of think about this is very similar to how humans behave. So let me say what I mean by that. So there is a solution here where the function value is -5. There's a solution there where the function value is -6. And so what happens is, as algorithms are trying to optimize, when they are at this point, it's hard for them to go to the other point because there's nothing in the vicinity that makes them move towards this. This is like having a large change in an organization and people hesitate to move, right? So algorithms are like people in that sense, that they need to see a continuous, simple improvement. They need to see that bread toasting in order to get from one place to another. And that's one of the difficulties that you have with non-convex optimization, because when you are at a place, you don't see where the best solution lies. So now, the way to sort of address that is to say, what about we add some more solutions to this space, right? So if we add some more solutions to the space, now the algorithms can start to see how they can improve and move towards that better solution. So this is what we call relaxations. So relaxations are ways of sort of encouraging algorithms to move towards better solutions without getting stuck in local solutions. And so more solutions actually allow for an easier search, and that's basically the main idea that relaxation construction works on. And a lot of these things that I will talk about are sort of motivated by how can you construct, how can you add solutions to your space in a way that that makes your search easier, but at the same time does not add so many more solutions. So I could go ahead and add so many more solutions to my space that the algorithm will completely get distracted and give me a solution that's not even feasible, is not implementable, and so on and so forth. So there is a trade-off. The question is, should I add solutions in a way that allows me to move towards the better solutions, but not so many that I get completely off track? So that's the trade-off that we deal with. So I want to talk about these three applications that I was initially mentioning. So for the separations, I've been working extensively with chemical engineering group, and David is quite familiar with some of the work that we've been doing there. And so we've had lots of students, but about 14 students and postdocs, but the work that I want to talk about is specifically was done with these two PhD students and Rakesh. And so what causes the non-convexity in that separations problem is two reasons. One, that there are about 85 million configurations when you go to 7 component separation. So chemical consists of, the crude distillation consists of 7 components, and you have 85 million ways in which this can be organized. Now think about the complexity of this, because so crude separation is a process that's about 150 years old. People have been improving this process through ingenuity over this period. And when we started to work with ExxonMobil on this problem, the general belief was that this was the best possible way that the separation can be done, because we've been improving it over so many years. There are two main reasons for the complexity there. Number one, that this 85 million configurations have to be searched through, but there's a second one, which has to do with the fact that the process of boiling and doing separations and so on and so forth is a nonlinear process, and how that ends up creating solutions is itself a challenge. So even given how you are separating a certain set of chemicals, you feed that to one of the standard process simulators that a lot of these companies use, like Aspen, and you will end up at a place that is not optimal for how that particular configuration should be operated. So even and I'll talk about that maybe a little bit later, but there are two main reasons. Discreteness, because of the choices in terms of what flows into what, and then nonlinearity because of the boiling processes. So both of these create challenges. Now, at the heart of the process is this idea that that somehow you want to add solutions to your space, but you don't want to add too many. So let's say there are only 3 configurations that you care about. So these 3 points represent the 3 configuration sets that you are interested in. That's all you care about. What you have done through your process is you have added all these other points and made this region much larger than what it was supposed to be. And now when I solve this problem, it says, oh, well, you should choose this configuration. But that's not a real configuration, right? And so how do I go about improving this, and how do I make it so that I'm actually discovering the real configuration that I can implement and practice? So the process for that, what it requires is to somehow remove a lot of the extra region that you had added previously. And there are some algebraic tricks that you can use for doing such a thing. Some of these involve taking constraints that were in your problem and doing some simple tricks, things that you would not think will improve the performance of your algorithms. You take a constraint and you multiply it with some non-negative quantity. That creates a nonlinear constraint such as this. So you multiply, let's say, with x1, x2, it creates a nonlinear constraint. After that, for these new nonlinear variables, you just introduce new variables and sort of go from there. Once you do that, you will find, and this is a short proof of why this actually works, I'm not going to go into that, But essentially, that would take away all the region that was useless and was not thing that you should have searched. And so you have to come up with techniques that will remove the regions that you don't want to search in. And that's part of the whole argument. So you want to get fewer solutions but maintain the searches. That's the crux of the move. Turns out that the standard mechanisms that exist for these type of things do not work so well in that distillation problem. We showed that there were some modifications. So if you sent this to the solvers that currently exist, this is your actual region, and this is a very small slice of that whole problem that I'm plotting. In that actual slice, the true solutions are in the set S. If you do what standard solvers do, you would be searching in this large region, which is not great. There are some improvements in the literature that would help you improve a little bit, but then we were able to sort of show that you can do significantly better improvements and get much closer to the region, which is why you're able to solve these problems today that were not possible to solve previously using these type of methods. So the end result of this was that if you took what was the literature before the work we were able to do, for 10% of the separations involving just 5 components, you would be able to take the state-of-the-art solvers, and these are the solvers which have all the enhancements and all the computing power enhancements. You would only be able to solve 10% of those cases. But with the innovations that we were able to do for reducing this region over which the search occurs, while not eliminating any of the good candidates, we are now able to solve all of the problem instances within a reasonable amount of time. What that has allowed us to do is take that crude distillation problem and prepare candidates for it. These are 2 candidate solutions, which reduce the energy consumption by about 17% and 16% each. Now, just to give you a sense, our algorithm generated these configurations and said, this is how you should be sort of doing the crude distillation instead of what was being done. And then the company went and did a whole simulation exercise to figure out what this configuration does. And each of those configurations took them about a month or 2 to run through the simulations to verify the results that we actually come up with. Because our models are approximate models. They're not the final models that actually work. So they were able to find that, yes, the simulated benefit was very close to what the predicted benefit was. And those are mechanisms that, and as I said, this 15% benefit would be amounting to about 285,000 barrels of oil each day. Yes?
What's the difference among those 3?
Yeah, so there are smaller differences. And one of the requirements was that, indeed, you don't want to make a huge amount of change because that's a pretty costly process for the company to make. So that was one of the restrictions, actually. But there are components that are sort of, you have components that sort of go through what is called a side stripper. We actually use a side rectifier instead of that. There are changes to some of the small flows and also how much you heat different types of fluids. So how much happens here changes relative to what happens here. So how much heat you provide and all sorts of things. So some process changes and some movement of rectifiers and side strippers. And that can lead to that larger benefit in terms of what you can do. So more recently, what we have been interested in is these are still fossil fuel driven processes. What we are now working on is trying to drive them completely through electricity. If we are able to drive them through electricity, that would be a huge reduction in the carbon dioxide emissions and so on and so forth. But that creates a new challenge because the problems become much harder now. what we found was that for all this time, we have been using fractional functions. They appear a lot in these type of problems, and they are central to, so a recent result that we had actually said that for creating these relaxed spaces with fractional forms, you should actually be looking at the problem in a geometrically different way, and that allows you to leverage a whole slew of polynomial optimization literature towards better relaxations for these fractional problems. Now, fractional problems have been studied pretty extensively, but this translation now allows for a much better result and has led to various improvements in retail operations, edge expansion problems, and so on and so forth. So, and various other groups have started to use these techniques at this point. This is sort of the main result, but it opens up possibilities now that we are able to say that 80% of the gap between the true solutions and the extra solutions is removed for up to 80% of the problems. And so, so that would allow for a lot improved possibilities. Similarly, what we have seen is that there are some problems that are in the discrete choice model theory. These are essentially what Luce, who won a National Medal of Science for some of this work, proposed a model for how consumers choose products, and essentially said that if your utility from this product is 3 and the total available products have a utility of 10, then your probability of buying this is 3 out of 10, something of that sort. And now the company is interested in which of these products to offer, and how much to charge for each of these products. And that problem turns out to be a fractional optimization because of this ratio that I just talked about. And it turns out that well-known literature results in polynomial optimization can improve how you can solve with these loose-type models in discrete choice theory and lead to 60% reduction in gap on these problems as well. My second piece is to talk about networking and how some of our work in that space has been also motivated by similar types of things. This is joint work with Sanjay, who's a faculty member in ECE at Purdue. And then the portion I'm going to talk about again in networking is some work that we did with a couple of students, one at DSP and one in ECE. So here, the problem is, if you recall, my question there was, you want to sort of have the network service the demand for what you need while ensuring that that service level is maintained even if 5 links on the network were to fail. So how do you provide such certification guarantees? And so the main issues at the back end of this problem are that there is a limited amount of capacity on your network. So capacity constraints are very important. The second thing that must be done is flow balance, right? Because as a person sends some flow, that needs to reach its destination. It cannot, new flow is not created, and flow is not destroyed in any of these operations. So those are the types of things that are going on. But the question that you are really interested in is, what if the capacity on some of these links goes away? If the capacity on some of these links goes away, then you are going to be able to send less flow through those networks. And so that's really what this part of the equation is doing, essentially saying, what if some of the flow was not able to make it because of the capacity restrictions? Now, turns out that, and I'm not going to go into the detail of this, this is really more like a Stackelberg game, as we call it. Essentially, what's going on is you have an opponent, and that opponent decides to cut some of the links on your network. and then you get to send the flow the way you want to send it through the network, right? And you want to ensure that all that flow finds its way to the destination. So the game you're playing is the opponent chooses the links to drop, and then you have the flexibility of how you can route the flow through the network. So that's essentially a max-min type of problem. I don't deal with two-level problems, so I must make it into one level. There are ways to do that, and that's how we sort of went about solving this problem. How that is done is you want to send out as much flow as you can, but you can treat yourself as being constrained by these constraints, and you can use some duality theory to sort of convert this into a single stage problem. And when you convert it into a single stage problem, these problems end up having a specific form, which we call disjoint bilinear programs. Essentially, products of variables are being minimized or maximized over constraints on each of these variables. And so we end up with some problems of that sort. So now, how do you handle problems of this sort? These will occur actually in all sorts of Stackelberg games if you start to solve them using this type of, so where one decision maker makes some rules, and then the other has to play by that rules, but is trying to optimize their own output. So it turns out, and the reason I pick up this application to talk about this is that it turns out that there is an interesting way to sort of visualize this problem. In reality, computer networks, and this is out of some work that Google had submitted or presented at SIGCOMM, they don't read out flows completely. So networks don't fully read out their flows. They actually follow certain policies for rerouting. So they restrict how they read out their flows. For example, if a link fails, they will read out around it for using some fast reflow techniques. So what they try to do is read out under some restricted type of notions. What does it mean for the network to be restricted? What it means for the network to be restricted is that one of the players has their hands tied, right? And that's the following player, which makes the first player have even better result or becomes more powerful. That's like adding solutions to your problem, okay? That's exactly like adding relaxation solutions to your problem. So it turns out that the formulation that, for example, Google uses or was actually discovered in computer science literature, which is called oblivious routing for demand flows, is actually a relaxation scheme. Turns out to be weaker than some of the standard relaxation schemes that we can deploy on these problems, and we were able to show that result. And so it essentially said relaxations can actually tell you what adaptations are practical and certifiable, and how you can deploy them in practice. And that allowed us to come up with some new adaptation schemes. The problem, though, is that this problem remains hard. It remains hard to solve if you allow the networks to fully adapt. And we are slowly moving towards that regime. As the world is moving towards more and more adaptivity on networks, we're moving towards a scenario where we would need to be able to adapt to these type of things. Turns out that recently I was able to show that there is a very specific way in which you can improve this relaxation quality so that eventually it gets precisely to the set of solutions that you're interested in. So in M steps, you're able to converge in these disjoint bilinear programs to the optimal solution. What that process involves is sort of creating certain kind of polytopes and certain kind of rational functions and leveraging some of the results I was talking about previously, where we were dealing with fractions, to create new types of relaxations. This ends up also being related to problems in computer vision. So when you're sort of saying, I want to blend two images together, and I want to figure out how I can go from one image to the other. And maybe I have 3 images. How can I go from one image to the other, and how can I go to the third image continuously without having an issue? You're essentially trying to solve some kind of a problem involving combinations, and that's intrinsically what you end up also solving for trying to solve these disjoint bilinear programs. So whether it's Stackelberg games or computer vision, at the heart of it is a very similar procedure that's sort of at play. And the final one I want to talk about was pricing. This was joint work with former colleague here, who's now dean at University of Arizona, continuing to work on this, and a PhD student. And so in this problem, remember we were trying to figure out how to price things. We set up this problem by saying what is it that the supplier is trying to do, as John was asking. It's trying to set up a system where they maximize their profit, ensuring customers buy what is most profitable to them. And then that's the kind of setup we are trying to solve. So pricing when users are choosing the products. Turns out, and this is one of my last things to say, turns out that we find that this particular problem, when you have those customer orderings, so somebody likes ice cream much more than another, those type of setting, you can solve this problem as a network problem where you're just, it's the same as trying to find a shortest path on a given graph. So the problem is one where you set up a certain type of graph structure and you can identify the best solution by trying to find its shortest path. Surprisingly, we find lots of surprises from this type of analysis. This has been an open question for finding how to price. We find that people are willing to pay more, and yet the supplier or the vendor loses money.
Just to make sure.
Yes.
Say willingness to pay increases.
Willingness to pay increases.
All.
For all consumers.
But profit for the vendor
Decreases, yes. And that's in the optimal pricing scheme. So you do find things of that sort. You find all sorts of, because there is this notion of non-convexity that comes into play at the back end of some of these. And we had to actually go into a higher dimensional space to write this as a shortest path problem. So it ended up creating some interesting insights into a variety of different things. Why is that?
Yeah, I'm trying to.
So it's because, and once you see why it occurs, the reason for it is the relative pricing does not. So I'm not saying everybody wants to pay more, yes, but the customer who buys the product for us. So think of a customer who wants to buy 4 scoops of ice cream, right? Right? Yeah. So who wants to buy 4 scoops of ice cream? Their value for
Breakfast.
that's just for breakfast. So their value for buying 1 scoop also went up, right?
Okay.
Now you're selling 1 scoop of ice cream to somebody else as well, right? And their value also went up slightly, but maybe this person's value went up more, right? So when you try to offer that 1 scoop to the person who doesn't value ice cream as much, your price for 1 scoop is not so high which means now you have to worry about the person who likes 4 scoops moving over to buying 1 scoop. And you can't extract all their increased surplus. In fact, you have to reduce because they have a better possibility with 1 scoop. So you can't extract as much surplus out of them.
Well, I apologize, I'll ask later, but I don't see
Yeah.
everyone being willing to pay more.
Everybody is willing to pay more, except that the gap between, so you offered it for $5. This person really wanted to pay $10. So now they are getting a surplus of $5 from a product they did not buy. So the product they did buy, you cannot charge them too much.
I'll have to think about it.
Yeah. But there's a bunch of these type of things that end up happening in these models. Wanted to acknowledge support from a couple of different grants, NSF, AFSR, Department of Energy, and ExxonMobil on some of this research. Wanted to leave you with a few thoughts. So non-convex optimization, similar tools apply to a wide-ranging set of applications. There are significant advances in computing, but even much stronger advances in algorithms, which make these things possible. Relaxation techniques are at the center of a lot of this. Judiciously add solutions that help the search for better solutions. 3 types of advances. The 3 applications I picked were primarily to show there are numerical advances which allowed us, for example, in distillation to solve problems. There are new policies that we can come up with through relaxation techniques for network design problems, and at the other end, there is tractability status for pricing type problems that can be solved primarily by looking at some of these type of techniques. I think these are some of the things that can help us with sustainable future, resilient system design, and strategic economics. Challenges abound, but hope sustains. So, with that.
Thank you, Mohit. We have time for questions.
Still don't understand. Go ahead.
Yes.
Oh yeah, I have a question for the last part for pricing. Do you consider assortment selection meanwhile deciding the price?
Yeah, no. Not in this. Not in this. Yeah. So the only assortment. So there are only 2 things happening in this pricing model, right? One is you're pricing bundles of goods. So and these are cardinality bundles. So these are bundles of quantity discount problems. So if I have 6 units, what price should I go? 3 units, 7 units, and so on and so forth. So that's one class of problems. The other class of problems that we treat are those where there's a quality metric. So you're sort of producing the software which has higher and higher. So you offer a mega version to one person, half or less featured version to somebody else, and so on and so forth. And there's a single dimension of measuring that quality. So those are the 2 settings. We're not selecting an assortment during that process. Yes. You still have that question.
Separately. But it seems like if everyone is willing to pay epsilon more, why not increase the price by epsilon?
Yeah. Everybody is willing to pay epsilon more, but somebody is willing to pay 5 epsilon more. And so
Price by epsilon.
you increase the price by epsilon. Now they feel like they lost 4 epsilon
You lost me on that.
because they're surplus, right? So this is the alternative option for them. So because you increase the price by epsilon, they still had a margin of 4 epsilon on top of that, right? And they're like, oh, should I switch to that? That's where I'm getting a larger surplus. But you were selling them a much more expensive commodity. So now that they have tendency to move towards this cheaper commodity, you can't charge them as much for the larger commodity.
So you have multiple consumers, but also
You have
multiple products.
Multiple products and multiple.
Where you left out of your, sorry.
Yeah, no, so I guess the multiple products part, matching the multiple consumers. If there is only one product. I
Yeah,
guess
so this is
you could
bundles.
just- But because of multiple products, that's
Yep.
where this
That's where the
paradox.
problem. Yep. Yep.
You left that part out, I think.
Now this is the bundle. So it's still one product, but it's 4 scoops or 2 scoops or 3 scoops, right? So that's what the different products are. Or the quality, as we were talking about, the software at high quality, medium quality, or lower quality. But for everything, people are only willing to pay more.
Yeah.
Yes. And still,
Yeah.
yeah.
So if, I'm gonna ask a question about the
Ask.
numerical capabilities of the computers these
Mm-hmm.
days. Again, it shows, I haven't been working on this extensively as I wanted for years now, but are you saying that the computing power is at a point now or soon will be at a point where just exhaustive search and even forget about relaxation,
Yeah.
just do the exhaustive search will be fast enough?
So that's why I said that the computing power is only increased by a factor of 2,000, right? While the algorithms is the one that actually is driving the majority of the change. So the fact that we actually can build these relaxations is what is driving the ability to solve these problems. So today we solve TSPs or whatever with 5,000 cities. There's no way we could exhaustively enumerate those, no matter how much computing power we had.
For the relaxation, you're talking about relaxation that would introduce inaccuracy, or you're talking
It will,
about
yes.
Right. So
And
whereas the
the-
computing power does not carry that loss. It's
No,
not
no,
relaxing the problem.
So the part that I did not talk about was the fact that after this relaxation produces a solution that's approximate, how do you actually get to the true solution? And the way you do that is you solve a divide and conquer approach. So you sort of solve problems on smaller regions that are where the relaxations become tighter and tighter. And that's how you actually solve these problems. So relaxation is still the key element as you solve this whole problem. So certainly when we solve the distillation problem, we can't solve it in one shot. We still have to do that divide and conquer piece to actually get to the solution.
Any other questions? Please, the last question.
I guess I was thinking of supply chain resilience. So do you think some of these things can be used to design supply chain?
Yeah, so I did not talk about some of this stuff that we've been recently doing. So one of the questions that we've been trying to solve recently is building AI models for doing routing. So you can sort of take the technology very similar to what is used in, let's say, ChatGPT. You use similar transformers and stuff like that. Now you can replicate the performance of some simple optimization schemes using these AI mechanisms. With that in place, if we are able to replicate that, what we've shown is that for designing these type of systems, these can now be trained with data and start to perform better in terms of designs, right? So certainly this problem also occurs in logistics, right? This is a multi-commodity flow problem. I'm sure you're familiar with that. So this is a multi-commodity flow problem that we are now trying to do optimization over. So you can take exactly this. Amazon has some interest in this type of stuff. They're talking to us, but their interest is more on can we actually replace the optimization piece with the AI so that you can then optimize the design. And the AI acts like a function rather than a solver. So that allows for certain things that are not possible with this mechanism. So we are looking at some of that.
Well, thank you so much. Thank you, Mohit. It's been a stimulating talk.
Thank you.